All right, so I'm going to explain step by step the process of converting an rs485 signal into J1939 and vice versa. All right, the problem. We have a network that uses J1939, and we want to integrate these rotary sensors, these rotary encoders that only talk in rs485. So we're using these AMT21 version E. Version E is the one that has an adjustable baud rate. It's a 12-bit resolution and is a single turn encoder. And the way they work is that they have two internal registers. One is to hold the hard-coded ID of the device, and the other, when it comes to the E version, the other register holds a 2-byte value representing the position of the axis which has been turned. So we can measure angles with this, and we use the rs485 protocol for that. The way it works is as follows. We have four rotary encoders. Each one of them has a unique ID, 14, 24, 34, and 44 in hex. And of course, each one of them holds the position of its axle. If we want to get the position of the guy at ID 34, we just send a single byte and we wait for a respond. So the single byte goes onto the bus. Each one of the encoders receives it, but only the one that has the corresponding ID will put its data bytes onto the bus to be received and read. Now, these bytes are coming in as a bit stream, and the first bit encountered will be the lowest bit, yes, it'll be the lowest bit of the lowest byte. So we get the low byte first. So there's a couple of conversions that need to be done. First, we have to get rid of the last 2 bits of that package because they are used for checksum. Then we pad them with zeros. Then we inverse the bits. After that, we have to place the bytes in the correct order. I think they come in little endian, and we have to read them in big endian. And since it's a 12-bit resolution sensor, we have to shift the 2 bytes by 2. And as we can see here, the result is E79, which has a decimal value of 3,705. And if we map it, this value is mapped from 0 to 495. So if we were to map it to 300, from 0 to 306 degrees, this would be 325.71 degrees, 0.71. And what we do, so this is the routine for reading a single sensor. What we have to do is repeat that 4 times, and the Arduino microcontroller will be doing that. It'll just ping each one of these 4 sensors and retrieve their data bytes, and we'll place that onto a CAN payload to be received by anybody on the J1939 network. And that's how the conversion goes between rs485 to J1939. Now there is also another function that is to zero out the sensor. And according to the spec sheet, if we want to zero out sensor at ID 54, we have to send 2 bytes. The first byte will be the ID plus 2, so 56. That will signal the sensor that the next byte will be an extended command. And if we send 5E, that'll be the command to zero out the sensor. And the way I handled it was to use just 4. I'm sure I could just use 1 byte and just read the bits that have been flipped. But to make it simple, I'm just using 4 bytes, and byte 0123 will correspond to sensor 0123. If the value of that byte is more than 0, then we want to zero out the corresponding sensor. In this case, the second byte has a value of 1. The microcontroller will read that and will know to ping our second sensor, which has ID 24, and it'll add 2 to the ID, so it'll send 26 plus the code for the command for zeroing out that sensor. For hardware, I'm using an Arduino Mega, an MCP 2515 for CAN communication. It uses SPI to communicate with the Arduino. And this is an rs485 to TTL chip. And yes, it can read up to 128 slave devices. We're only using 4. And I'm only using um, uh, one serial COM on the Arduino. This way, as you can see, I'm using serial 3 to communicate with the rs485 chip, and on the other side we have the rs485 bus. The 4 sensors are placed on the bus and everything is powered from a single source. The Arduino will provide the 5 volts out to power the rs485 chip, the 4 sensors, and the MCP 2515 CAN module. As we can see, it uses 5 volts and it uses SPI communication. The interrupt pin, if held low, will make the module write CAN, and if it's held high, it'll read from CAN. Anything else I want to say about this? No. Oh, yes. So, as we saw earlier, one thing I noticed is the time it takes to ping all 4 devices. I must have a 1 millisecond wait between sending a ping and receiving the data bytes. And I'm doing that on every millisecond. So it adds up. And right now it's adding up to 1, 2, 3, 4, 5, 6, 7, 8, about 8 milliseconds to do the whole pinging to gather the bytes of data for all 4 sensors. Now, if we want to go faster than that, I tried reducing the wait time. It just makes everything break. Things don't coming, the data comes in out of sync. So I would be pinging 14, but I would be getting 24's data bytes back, and things would get messed up. If we want to go faster, then instead of using one rs485 to control, I guess, these 4 sensors, the Arduino Mega has 4 serial ports. So we could technically have each individual serial port connected to an individual rs485 chip and a single sensor. This will definitely reduce the it's going to take about 4 milliseconds to do the whole thing instead of 8, because I have to still send and receive. For sending and receiving, I would take only 1 millisecond, 1, 2, 3, 4, and an extra one for writing to CAN. So it'd be like 5 milliseconds altogether. And there would be no issues of getting the wrong bytes, since each sensor will be connected to a different serial port. If the data is not back on time, then it's just going to use the latest received byte, and it wouldn't be for sure. It would know for sure that it's coming from the appropriate sensor. Okay, so now let's look at the system working. Let me change my scene here, put this back to the back there. I can just plop. All right. So here we have the PV780. I have my Arduino Mega at the bottom with the RS485 chip, and There's a single bus for all of these four sensors, sensor A and B, C and D, and they are represented. This gauge will show sensor A and B. B is in green, in orange, and A is in blue. And the other gauge here is for sensor C and D. So let's move it out. Let's see. It goes all around 360 degrees. The one thing I implemented just for debugging, I noticed that the two stacked sensors do not generate the same bytes, even though they're all physically connected to the same axle. And there is a few ticks of difference, and I convert that to degrees. So right now, it's the two sensors are off by 0.26 degrees, and the difference gets bigger as we spin faster. And I'm also recording the largest, the max difference recorded. So right now, the largest difference, I was going crazy, was, yeah, see, 1.495 degrees. And that's the other sensor, the other stack of sensors goes 360 degrees. And let's look at resetting them. So zeroing them out. Oh, my laptop is in a weird angle because I'm using the internal camera. So I have to use my entire laptop. And let's see, we send, and we're zeroing out sensor A. Let's zero out sensor B. Any value bigger than 0 and less than 256, I guess, of course. Let's do a 9, whatever. Send, go. Now let's do all four of them. There we go. And now they've been zeroed out. It doesn't matter where these cables are completely interchangeable since all of the sensors are on the rs485 bus, and we'll just wait for an ID to respond. So as we see here, this one will still work. This one will only move one since we only have one connected. And look at what happens when we connect the second one. Since they are both physically connected to the same axle, as soon as it powers up, it will broadcast its value. So boom. Now what can I wanted to show the original way to reset these sensors was to basically use the software that came with these sensors. So I'm doing it for this one. It has to be connected to some conversion rs485 to USB. So we'd have to plug in a laptop to zero out this chip, and you would have to use their software. This is where you can set the hardcode the node's ID and set the baud rate, but also align. So as you click align, it'll take a couple seconds to get this guy to align. Did it do it? It didn't do it. Oh, okay. Well, let's move. I thought it should be down to 0. Yeah, there we go. Now I did it. Yeah, as I move, it's kind of loose. It needs to be fixed properly. Otherwise, the little disc kind of wobbles inside. And yeah, so I figured leveraging CAN for the reset would be more user-friendly. Let's do that again. Reset this guy, this guy. Let's reset all of them. with one CAN message, everything gets reset. And that's about it. That's the whole system. And I can have more details later. Can't think of anything else. I don't really want to go over the code for this. There's, depending on if we want to use 4 serial ports or a single one. Um, yeah, I basically have a queue of the 4 devices, and well, the code is pretty self-explanatory, so I'm not even going to go into that. Um, yeah, oh yeah, maybe the PV780 is set up in a way that reads, let's see, can I zoom this out? So on the PV780, let me put this up front. There we go. Let's say this gauge here is going to wait for a variable to change. The variable is sensor B12-bit var, and that will be populated by this PGN setup at FFFA. We have these 4 variables that correspond to the 2 bytes to the 2 bytes received from each sensor. And by code, I will read the content of this variable, which is the content of these the first 2 bytes. For example, this is B. So I create a double. I read the variable that we just saw, the sensor B data 12-bit, put that into the variable that I just created, and then write that variable to this user created sensor B12-bit var, which is what drives the UI. And yeah, that's about it. Ultimately, we could set up the PV780 to send the zero out message. I could probably do that tomorrow. Yeah, I will have the PV780 send the zeroing out message to zero out the sensors. And that's about it. Thank you for watching, and I'll have a printout of all of that for the meeting. Thank you, and bye.